target code generation, the overview discussions that we started yesterday. So we will just continue on that, and I have, let me get to the presentation. Somebody please confirm that you are being able to see the presentation.
Yes, I can see.
Okay. We discussed about varied kinds of 3-address code optimization in the last class, the opportunities for that, not exactly the techniques. We will do the techniques in the subsequent modules. And then we talked about creating the memory binding. Creating memory binding is basically associating an address expression with every variable and parameter and compiler temporary that exists. So taking from the tree of symbol tables, we flatten out and create the layout of the activation record for every function, and an example we discussed for that. So besides that, there will be other bindings created for the global symbol table, which is not activation record. It is going to be there available to the program for the entire duration of the program, which will also use data segment. Then there could be others like table of content and so on. Now, besides the memory binding for variables in the memory binding for the variables, there would also be register allocations, because as you have seen that most of the assembly instructions that are to be performed, that is what the 3-address codes will get translated to, actually use register. So if a variable is residing in the memory, then it will have to be copied to a suitable register, which is the load operation. And then at that point of time, there will be 2 copies of the variable, one in the memory, one in the register. Both of them will have the same value. And then we'll do certain operations in the assembly with the register. And when the result for the variable is ready, then at that time we are to write it back to the designated memory location where that variable should exist, because by the operation the register and the original memory value have become different. So we copy the value back from the register to the memory, which is the store operation. Now naturally this means that we need to associate or make registers available for doing this load, store, and the compute operations. It could also be used for passing pointers or passing the return value and so on. And the fact that there is a limited number of registers in the system, it means that the registers need to be regularly reused. So I just show an example here, continuing on the same code, to show that how registers can be required. So we on this code we do a very simple def use analysis. Def use analysis is where that variable is defined, and up to what is the point where the variable is used. So a variable is defined when something is assigned to it, and it is used when its value is used on the right hand side. Now this the duration from a definition to the last use of that variable is kind of the life of the variable. During that time, the variable remains, the value of the variable needs to be remembered, and that is what is called the liveness. So here I show a very simple technique which is often used to compute the liveness of the variable. So if you see the code here, you will see that within this code, the value of a and n, both of these are used, and they have not been defined. So naturally, when the code starts executing, it must be that there are valid values in a and n. So there is something that has happened before this code, by which the value of a, which is the base address of the array, and the value of n must have been set. So in the comment on the right, I show the variables which are live. So when the code starts, a and n must be live. That is, they must be having certain valid values. Then in the next instruction one, an assignment is made to s. So at this point, s is getting defined. And once it gets defined, it remains available for use. So we include s in the liveness list. So at 101 and at 001, three variables a, n, and s, three variables are live. Similarly, at 102, I is defined, so I becomes live. At 2, at 3, I and n are being used. So to be used, they must be live at that point. That is, they must have been defined before. So here the liveness does not change because nothing is being defined further. So the liveness remains same, a, n, s, I. And that goes on as you go through 4, go through 5, go through 6. But in 7, a new variable T1, which is a compiler temporary, is getting defined. So T1 becomes live. Then in 8, another user-defined variable T_1 is also getting defined. So you can see how the liveness list is increasing. In 109, nothing is defined, but also in 8, T1 is being used. And if you see carefully, you'll see that at 7, T1 is defined, and at 8, T1 is used. And beyond that, there is no other use of T1. So no matter what the values of a, n, and all of other variables are, the variable T1 after 8 has no use. So you can see that at 9, I have dropped T1 from the liveness because it is no more live. Its use is over. Similarly, at 8, T_1 is getting defined and used at quad 9, and it is not used anywhere further. So at 10, T_1 is also loses its liveness. It becomes a dead variable because you do not need to remember its value. But s and I remains live. You can question as to why does a and s, I need to remain live, because as you go through, you do not see their use, but you can understand that I have a goto here. That goto takes me to L1. So after 10, I will actually logically execute 5. So when I go to execute 5, I need I. So the value of I was computed in the earlier iteration must be required at this point. Therefore, at 10, I has to remain live because whatever value it has a further use in 5. So it is to be remembered that the liveness is not only based on the forward progression of the code. If there is a jump back, the liveness will need to be carried forward. Similarly, S will have to remain live because going to L1, it will eventually come to 9. So after even after the quad at 10, at 9, S will need to be used. So S will need to remain live at 10. When I go back to 3 eventually, from quad 6, by go to L0, N will be used. So N also remains live and so on. And this continues till the loop goes on till I actually hit quad 4 and jump to L3, at which point I no more need A, N, and I, but I need to return S, so S has to remain live. So this simple analysis, I mean, it's not simple, but this analysis, we'll see how to do this analysis, tells us at every point what are the variables which are live. And based on that, I form a linear graph called an interval graph, which on the x-axis show the quad numbers, and the lines show for every variable the starting and ending quad number of how long the variable is live. So A is live from 0 to 10, N is live from 0 to 10, S becomes live at 1, so it is live from 1 to 11 till the point it is live, whereas T1 is live only from 7 to 8. So you can see how the intervals are. So these are the intervals over which it is live. So which means that if I have to keep the variables in the operations, for each variable I need a separate register. And what is the maximum number of registers that I will need for this code if I am not reusing a register? That is, computing in a register, storing the result back, and then again loading it at a later point of time when it is needed. So that you will get by simply if you draw a vertical line and see how many of the horizontal lines are intercepted, you know how many variables together are live. So if you draw it at 0, you know that you just need 2 registers. At 1, you need 3 registers. Whereas at 5 also you need 4 registers. Whereas in 7, you need 1, 2, 3, 4, 5 registers. At 8, you need 6 registers, and so on. So if I have up to 6 registers, then I can do this whole computation without writing back the result. So this is the basic register allocation problem that in general I will not be able to have maybe as many registers as I want. I may want to generate the code for this without actually having 6 registers. I may have 4 registers. So if I have 4 registers, I have to decide which are the variables which must reside on the register and which are the variables which I can copy into the register, load, do the computation, then store it back to the memory, and then load it again when I need. Right? So that's the kind of analysis that happens in register allocation, and that's a big issue that we will talk about. So I'm just illustrating the issues in target code generation. So we do DFA and all that for that. So these are the steps as I have explained. Now, after the registers have been allocated, I will still need to actually go ahead and generate the code. And for that, for every function, I will need to generate a prologue. And you have seen that in Professor ISG's lecture. Professor ISG's. Is anybody saying something? Okay, no. So this prologue includes saving different registers before use, setting the base pointer to the right point, and so on. And only after that, the actual code can be placed, the code of the computation of the 3 address instructions. Similarly, at the end, I will need an epilogue part of the function code, where the registers will have to be restored for the caller. We have seen examples of this earlier, where I restored the registers, I restored the base pointer, stack pointer, and all that. So this will be the basic structure of the code. So you take the TSC, optimize, in several different ways, create the memory binding for having the layout of the activation record, perform register allocation to decide at which point what kind of registers, which registers can be used, what load stores are used, and then create the prolog and epilogue of the functions, and finally put the code of the 3 address instructions. Now, for doing the 3 address instruction, what you need to do is for every instruction, you have to choose an optimized set of assembly instructions. And for example, why do I say optimized set of assembly instructions? For example, if I go back to the code, you have here in 5, I assigned I plus 1. Now, naturally, this code can be translated by keeping I in a register and then adding 1 to that. Naturally, that is, and then writing it back to I. So this will be perfectly logically okay. But many of the assembly instructions, assembly language will have an increment operator, which is in hardware implemented in a way so that you can very quickly do the addition of 1, because that is very frequently required. So that will typically be a single cycle operation, and we might, if we are trying to use optimized assembly instruction, we might use, in this case, an increment operation. Whereas if it were I assigned I plus 27, then we'll use the add instruction. So we will use these different kinds of choices, instructions for doing the actual translation. We could try to use algebraic simplification, reduction of strength. We have talked about this earlier. There could be different machine idioms. In certain assembly, there could be certain ways to write a type of code. So these are the different issues that we will look at. And once this assembly code has been generated, then again, we will do another round of optimization, which is on the assembly. For example, there could be several redundant load store. You may have stored a variable and then loaded it again, but in between, maybe the register was available. So you could have avoided that store and load back. So there could be unreachable code that gets generated. Flow of control can be optimized in multiple ways. So these are different examples that we see. And this optimization is at the target code level. That is, it is happening in the assembly instruction itself. Right? So these are the broad steps that would take place. And finally, we will put this assembly file together. And for linking, we will, particularly if there is multiple source being built from multiple translation units, multiple files, then we will need to create the external symbol table and the link information. So this is the whole process of target code generation. I've just given you an overview here for this purpose. And finally, there's a code mapping in terms of for different 3 address code. I've given the typical assembly that you might want to use. But of course, this is nothing sacrosanct, and in general, you will see that there could be various different variants that you could use for this. But this is just one very direct, simple way to generate some code that runs. So without optimization and so on. So for very typical copy and unary and binary operators, unconditional and conditional go-tos, and for function call and so on. I have just given here, I'm not going through all of this for array access. I'm not going through this. I've just given this as a reference for you to use or refer to in case you are having difficulty in understanding how to translate a 3 address instruction into the. So this is the overall target code generation process. Let me stop here for a while and see if there are questions.
PPT, I could join finally.
Oh, great. So you could join through your mobile network?
No. Through the institute network only. So I think they have rectified.
Okay, good. Okay. So we just finished the discussion on the target code generation overview, and
Yes.
I'll move on to the next module. Okay. So friends, now I will move on to discussing into different of these strategies that we have talked about, so that we know how to actually do these different optimizations and register allocation and code generation and so on. So each one of them we will take up in certain different module, because each one is significantly elaborate in that process. I hope the presentation is visible and I'm audible too. So the first that we discuss about is a new intermediate representation, or a new representation of the code called control flow graph, and we will see how it can be used in local optimization. We will explain what is local optimization. So we will talk about the optimizations, different types, and we'll talk about basic blocks and control flow graph, and how to do the local optimization. This is outline. So some of these we have discussed already. The intermediate code generation process introduces efficiencies. We need inefficiencies. We need to optimize on that. We have seen examples. And code optimization will remove all of that. The changes in the structure of the programs could sometimes be such that even after you see the optimized code, you may not be able to actually recognize the original code, because I may have inline functions which have expanded. I may have unrolled loops, and I may have eliminated some of the programmer defined variables because they may not be required. So we will go through all of these processes. And optimizations are typically classified as local or as global. So I start with the same earlier example. We have seen this. We have seen this code, the address for the specific vector product. And in this, these are the kind of people optimizations which can be done. You can eliminate redundant instruction. You can eliminate local diffuse of temporary. You can eliminate unreachable code. You can eliminate jump over jump. All these examples we have seen. Algebraic simplification, strength reductions, and so on. We have seen examples of most of them. And after we do this, this is a people optimized code that we have already seen, where different temporaries which were just locally used in the local context, they have been optimized out by just propagating their values. And from 130 instructions, with that we came to only 25 quads. So 5 quads we could eliminate. We could reduce strength in terms of multiplying by 4 by using left shift operator by 2. Now, all of these kinds of optimizations are called local optimizations, which are carried out within basic block. We'll formally define what is a basic block. Conceptually, a basic block is a piece of the code where you have a unique entry and a unique exit. There is no branch within a basic block. So the advantage of dealing with basic block is that once you enter a basic block, you know that surely you will exit with the unique exit point. And therefore, you know uniquely as to what is the sequence of executions that are going to happen. So within that, you can eliminate local common sub-expressions, that is called local common sub-expression elimination. You can propagate and fold constants. You can eliminate def use of temporary. We have done that. You can eliminate dead code. We have seen that. Reorder some of the computations and so on. So these are some of the local optimizations that you can do. On the other hand, when you look at optimizations which are not limited to such basic blocks, you have a global optimization. That expression could be common between two different basic blocks. It is defined in one and it is recomputed in another. Now, when you do that between two different basic blocks, the issue is, will the expression be computed every time when you go through this computation process? Because they are on different basic blocks. So it is not necessary that you compute in one basic block and it is available in the other basic block. And a similar set of considerations go on for all these different kinds of elimination of unreachable code, jumping over jump, jumping onto a jump, def use of temporary, and so on. And we will see code loop invariant code motion. We have talked about loop invariance in the earlier module, and we will talk a little bit about loop unrolling and so on. So there is a whole class of global optimizations. You may not be immediately being able to see all those what they are, but just have patience, and we will come up with examples to explain them over a period of time. So let me formally define basic block and control flow graph. A basic block is a sequence of intermediate code with a single entry and single exit. So it starts at one point, executes the code, and goes through at the other end. And a control flow graph is a graph where the control flow of the program is shown, but you use the basic blocks as your nodal units in that graph. That is, it is a directed acyclic graph where every basic block is a node, and you show the flow between the basic blocks, and you do optimizations on the basic block. So this is what the definition is. Just try to remember that a basic block is a sequence of code which has a single entry and a single exit, and in a way it is a maximal such. So kind of, if you include any further instruction, then it will not remain a basic block. If you include any further quad, it will not remain a basic block. So let us look at an example. So this is the code is shown on right, which is a simple code to compute inner product of two. Assume that they have been defined, all variables have been declared, defined. This is the corresponding 3 address code. So you have prod and I initialized with initially given value 0. Then you have this loop where you compute, first have to compute AI. So you do 4 star I, and then in T2 you get AT2, which is AI. Similarly in T4 you get BI. Then you make the product of them in T5 and add it to prod to get T6. So T6 is the right hand side of this assignment expression of the vector product. And then you assign T6 to prod. And having done that, you pre-increment I. So you do I plus 1, take it to T7 and assign T7 to I. And then finally, you have the condition check for the while loop. where you take I, checking for I less than 20. So if I is less than 20, then you go to L1, go back and do the loop. So you come to the beginning, which is computing the I. So this is the loop back. And if it is false, you go to stop. Now, instead of writing it in the linear, just keeping it as a linear code, I have actually blocked them in terms of groups. And if you look at these groups are what are the basic blocks. Because, for example, if you look at P1, then if the control starts at the beginning, it has to do both prod assign 0 and I assign 0 before it can flow out. So it's a single entry and a single exit. Similarly, if you look at B2, whole of this B2, once you start at L1, there is no way but to end in the if condition. So it has a single entry here and a single exit here. And then you have a loop back, which is the control of do while semantics. And you have another possible exit. From the single exit, you have another possible target that if I is not less than 20, then you go to stop, which by itself is a single basic block. So what I show here are the fact that this flat code that will get generated from the translation of the simple C program will actually give you a set of 3 basic blocks. And you can look at the whole control flow in terms of these basic blocks, because in the whole basic block you can take as one unit, because the control enters at one point and exits at the other. So you know decisively that the control cannot go here and there. So the control flow can be shown only between the basic blocks, and that's what we are doing at this point. So this is a flat code which is now being shown in terms of this graph, and this graph is what we call the control flow graph, or the CFG. You will see that the beginning quad of every basic block has been highlighted in red. These are highlighted in red because how do you identify the basic block? To identify the basic block, you try to identify the first statement of a basic block, or the first quad of the basic block, and which is called a leader. So we have highlighted the leaders. So once we can highlight the leader, then a basic block is from one leader to the next. So that's the simple algorithm. So let us look at how we do that. So we will determine a set of leaders. Just give me a second. I have something to attend. Okay, I'm back. So we need to determine a set of leaders. So what is the base logic of a basic block? Is that control will enter at one point and exit at a unique point. So the leader, which denotes the beginning of a basic block, could be any one of these. At any quad which satisfy one of these properties will be the leader of a basic block. Why? Let's see. Obviously, the first statement of the program is a leader, because a basic block has to start here. There is nothing, no surprise. Now, any statement which is the target of a conditional or unconditional go-to is a leader. Any statement which is the target of a conditional or unconditional go-to, surely, because if a quad is the target of a go-to, then that is an entry point. And we have said that within a basic block, you cannot have more than one entry. So it has to be the beginning of a basic block. So if I have a statement which is the target of a go-to, it must be a leader. It must be the beginning of a basic. Third, any statement which immediately follows a conditional go-to is a leader. Why is that? Because if a statement immediately follows a conditional go-to, then it has a unique entry from the failure of that condition. Right? So it cannot be considered as a part of the earlier basic block because you have a conditional exit. So the earlier condition of a statement being the leader, because it's the target of a conditional or unconditional go-to, defines the unique entry to the basic. And the second condition signifies that you must have a unique exit from the basic block. So any statement which immediately follows a conditional go-to is an exit. So it has to be a leader. Then once you have identified the leaders, then all the leader and all statements which follow it in the sequence of the quads, but do not include the next leader or the end of the procedure. Any statement, any sequence of statements that starts with the leader and follow up to the next leader, but not including the next leader, is the basic block corresponding to that leader. So there will be as many basic blocks as there are leaders. And any statement which may not have been placed in a basic block obviously can never be executed, because we have seen how the control is going through in terms of conditional and unconditional go-tos or fall-through. So if after doing this, you find there is a statement which is not in any basic block, then that statement may be safely removed. Right? So this is the basic algorithm for a basic block. That's so if you look at here, if you look at this code, the linear sequence of quads, then prod assign 0 is a leader because it's the first statement of the program, condition 1. Then if you look through, then in this whole code, L1 is a target of a conditional go-to. This if less than 20 go to L1. So this is a target of a go-to, so it has to start a basic block. So this is another leader. After that, the control flows through, none of the conditions is satisfied till you come to I less than 20 go to L1. So by condition 3, the statement that immediately follows it, the quad that immediately follows it, which is stop, has to be a leader as well, because I less than 20 go to L1 gives you an exit of the basic block that was configured. So this simple example show that there are 3 leaders, and 3 leaders actually come from 3 different conditions. And once you have got these basic blocks, then you form by drawing directed edges from one block to the other. And a basic block will have a whole lot of information, like the number of spots in that block. It will have pointed to the leader of the block, because you have already know that. It will have pointers to the predecessors of the block, that is from all those points from where the control can come to that block. It will have pointers to the successor of the block, all those points where the control can go after this, and that will be the basic structure. So let us take an example and work out. I'm sorry. So this is our people optimized code that we had taken. Here for reference, I have written the 3 conditions. again to remind, the first quad of the program is a leader. A quad which is a target of some goto is a leader. Quad which follows a conditional goto is a leader. So n assigned 5 is a leader by the condition 1. So I've written the conditions. Now let us see quads as a target of some goto. So I will just check at the gotos. So here I have a goto 106. So the quad at 106 has to be a leader. So this is a leader by goto. I have goto 124. So the quad at 124, which is returned, is a leader by 2. I have a goto at 102. So this quad, if I less than, has to be a leader because I can enter at this. I keep on. I have a goto at 120. So at 120, this quad has to be a leader because I can enter at this. And there is a goto at 104, which is I assigned I plus 1. This also has to be a leader. So by condition 2, we get so many different leaders. And then I look for unconditional gotos. Conditional gotos for part 3. I have a conditional goto at 102. So the quad that follows it immediately, which is 103, has to be a leader. So 103 is a leader by condition 3. I have another conditional goto at 110. So 111, which follows immediately this, has to be a leader as well because there is a unique entry point at 111. So, and there is no other quad which satisfies these conditions. So I have got in total these many 1, 2, 3, 4, 5, 6, 7, 8 different leaders. So this code will have 6 different basic blocks. So now I am breaking the code. It is the same code in that sequence. I'm just breaking the code in terms of basic blocks. So I had a leader at 100 and I go through till I get the next leader and do not include that. The next leader is at 102. So therefore I go from 100 and 1. Next leader is at 102 where the next basic block starts. Go back. The next is at 124. So I have that as a basic block. Next at 104, I have the basic block. Next at 106, and that will go up to 110. 106 up to 110. Then I have at 111 that goes up to 11 to 119. I have at 120, the next basic block goes up to 123. And so these are the different basic blocks that we will have. You will see that I have just kind of made a shortcut of not creating a separate basic block for 103. I have just clubbed it with the basic block here because it needs to have it. Now once I have the basic blocks, I will now do the target of the control based on the basic block. So let's say if I take basic block 4, what does it have? It has at 110, it has a go to 120. Okay. What is 120? It has to be a leader because I have a target there. So 120 must be defining a basic block. So it is defining the basic block B6. So instead of 120, I say I go to B6. I'll go to this basic. Otherwise, what will happen? Otherwise, it will fall through. Otherwise, it will fall through. So here, I'm introducing a transfer of control to the basic block 5, which is the fall through, which is 111. So I will go to B5, which is by fall through. Similarly, if I look at B5, I come through and I have an unconditional go to 104, which is basic block 3. So I will have a control jump to B3. At B3, I have a go to 102. So I'll make that into go to block B2. So in this way, the jumps, conditional and unconditional jumps, which are targeting specific 3 address codes, are necessarily now targeting leaders of basic blocks. So I convert the target from the quad sequence number into the target of the basic block, and I specifically introduce go to in case of fall through. Like from B1 to B2, it is just a fall through. So in the graph, I will just have from B1 to B2 a jump, as if a jump from B1, end of B1 to the beginning of B2. So this is what is forming the control flow. So let us now look at it more in the form of a control flow graph. So I have B1 that goes to B2, so I have a link here. From B2, I have a link jump to B7, so there is an edge here, or to B4, so I have an edge here. From B4, I have a go to B6 or to B5. From B5, I have a go to B3 here. From B6 again, I have a go to B3 here, they're marching. And from B3, I have a go to back to B2. So what I've got is a control flow graph where every node is a basic block with the property that if the control enters, then it has to enter at a unique point. And when the control exits, it has to exit at a unique point. And then all control flow are basically edges between these different basic blocks. Stop at this point and check if there are questions on the basic blocks and the control flow graph. And control flow graph is going to be one of the very fundamental data structure in terms of actually expressing all types of control flows, and will give us a good hold in terms of what is linearly, what could be linearly traceable in that process. There was Jyoti, could basic block B2 and B4 be marched? Could B2 and B4 cannot be marched because there are two different edges going out. So when you are in B2, you do not know that you will go to B4. And if you march, then you might have an exit from B4 which is in the middle. What you will eventually see that B1 and B2 is a direct fall through. B1 and B2 and that is can that be marched? That cannot be marched either, because you have an entry into B2 from B3. So basic blocks are defined in a way so that they cannot be marched in that way, because that will lose the property that you have a single entry and a single exit. Now we will see later on there is a certain concept known as extended basic block, which are not just basic blocks but kind of tree of basic blocks, where some bigger nodes can be created, but that will come later. But you cannot simply merge any two basic blocks because they have been computed based on the leader, which is always an unique entry point to a basic block. Okay? So that's the basic. Any other question?
Nothing, it seems, the forum.
Okay, then let me continue. So we have in this way formed the basic blocks and formed a control flow graph. So now as we have formed the control flow graph, we can see the context of the local and global optimization very clearly. For example, let us take basic block B4 or basic block B5. In basic block B4, I can see that 4 star I is computed in T4 and 4 star I is computed in T6. And I know, being a basic block, it has to enter at the computation of T4 and has to exit at this if condition. So if T4 is been computed, if T6 is to be computed, T4 must have been computed with the same value of y. So I can very safely say that these two are actually common subexpressions. The same thing I can say in B5, that if T8 has been computed, only then T10 or T13 can be, T12 can be computed. And I can easily see that within this basic block, there is no change in the value of I after T8 is computed. So I can very safely say that 4 star I is a common sub-expression between T8, T10, and T12. There are opportunities of saying that T4 is computed in B4 and T8 is computing the same expression here, or T15 is computing the same expression. But I cannot, from the basic block, I cannot say that confidently, because before here it is just a direct jump, but it could take any path whatsoever. Basic block to the other. So and
There's an audio problem, PPT. The voice is breaking.
Of and I can start. So you can see that so
There seems to be an audio problem, PPT.
Yeah, I'm trying to hang up. If I cannot hang up.
Okay.
I see. Am I audible now?
Now it is better. Yes.
So I'll continue. So continuing, in within basic block B4 or within basic block B5, I can very easily reason that in B4, computation of T4 once done will be available at T6, or computation of T8 is done in B5 will be available at T10 or T12. But we cannot very easily argue that between T4 and T8 or between T4 and T15, because they are in different basic blocks, and I will have to check on the possible paths that can be taken from B4 to B5 and ensure that I does not change in between them, to be able to say that T4 is actually available at T8 and can be replaced. So you can see that the common sub-expressions can be locally replaced here in B4. T4 can be used to replace the computation of T6, or T8 can be used to replace the computation of T10 or T12. So when we do that, we say that this is this is local common sub expression, because I'm doing it within the basic. Whereas if I want to do it between T4 and T8 or T4 and T15, I have to go across basic blocks. And so that is what becomes a global strategy. We say this is a global common sub-expression. So you can say that there are differences in the local and global strategy. So typically, when we talk about local optimization, we are talking about optimizations that are limited within one basic. And when we talk about doing global optimization, we are talking about optimizations that can extend across basic blocks. So when we are doing local optimization, since we are within one basic block, with the advantage that the control flow is completely linear within that, we have very smart techniques, very smart algorithms to do that. And we will discuss one of those, particularly for eliminating common sub-expression, common local sub-expressions. Whereas when we have to do global analysis, global optimization, we have to do a lot more in-depth process, and we have to adapt to what is known as data flow analysis. That is, on the control flow graph, we will have to analyze, as the control flows, how does the data flow along those controls and which data could be available where. And for that same reason, say between T9 and T16, we had discussed this earlier also, we actually will have the same common sub expression after global common sub expression has been performed. So we will actually have C plus T4 here. We'll also have C plus T4 here, but we will not be able to globally optimize them as a common sub expression because they come on different parts of the control. So that's the whole basic idea of local and global. So for this module, as of now, we will just focus on the local optimization issues, local optimization algorithm, and we will do the first set of very common optimizations that can be performed at a local level within one basic block. So here, going from this point, please remember that our whole context is one single basic block, and we are trying to first optimize each basic block, and then we will apply that for all the basic blocks in the control flow graph. And once that has been done, then we will go over to doing a data flow analysis later and start doing the global optimizations. So here I've just shown an example piece of code actually here, and then I show a kind of representation of this code in terms of computation nodes, which is what conceptually is used in doing the optimization. So here what I do is every node represents a kind of value. We have done something similar in terms of in terms of the abstract syntax tree, but here instead of being a tree, it is a graph, and here we will take cognizance of the fact that the computation is actually happening. So to start with, we have nodes which have values and which have variables denoting those values. So A is assigned 10. So that is represented as a node 10. And we put a label A designating that this node is what is the variable A. The variable A is 10. So this is the representation. Then we have 4 star A. So we make 4. It's a constant as a node. And it is, what is A? A is this node, which currently has value 10. And we create an operation node star, operator node star, and we link them, which means that this operator is multiplying this left operand A, we have 4, with the right operand A. And we give it a label B because 4 star A is actually B. Then we have I star J, so we create an I node, we create a J node, we have a star node, and we give it a label T1 to show that it is I star J. Then we have T1 plus B. So we have T1 node here. We have B node here. We create a plus node with operands T1, left operand T1 and right operand B. And the label for that is C, because that is the variable where you get the value of the C. Then you have 15 star A. So we have 15 created here. A we already have. And we create a multiplication operator node and label is T2. Then we have D as T2 star C. So we take T2, we take C, we have D, the multiplication node here, and we have D. Now we have I assigned E. What I do is I do not create a separate node for E, because since I is assigned E, the value of I and the value of E are going to be same. So what I do is, and that is a smart thing being done. What I do is I simply label the I node as E. So this means that I and E have the same value. Now I have T3 gets E star J. So I have J. I look up E. If I look up E, I get the same node, which is I. And I do a star. I already have a star between them. So I identify that between I and J, there is already a star. So it is the same node. And I put it a level T3. I put a level T3. So you can see now that the star node has two levels, T1 and T3. What do you conclude from that? What you conclude from this is that T1 and T3 are basically the same value. You can see here, T1 is I star J. I have copied I to E, denoting by giving an additional level to level E to I. Then I looked up E, I looked up J, I did a star, and I already had a star between them, multiplication between them, called it T3. I already have a level T1, so that T1 and T3 are basically the same. So you can see that this simple representation tells you a way to find out what is a common sub-expression. So what we have actually done is, even though they do not look to be same, it is I star J and it is E star J, but in terms of this basic block, they are at this point basically the same expression, T1 and T3. Then I get T4, which is I star A, which is what I have here. T4, I have I have A. I have I here, left operand A, right operand, call it T4 by star. And then we have C, which is T3 plus T4. So I have a plus T3 plus T4. So I have a plus created here. And this is going to get a level C. Now I already have a node having level C. So what does this mean is, when C is assigned here as T3 plus T4, then actually that earlier C gets invalidated. That earlier value of C is lost. So I designate that by crossing it out. So this is just graphically showing a way as to how can I keep trace of the computation that would happen in a basic block in the control flow graph, and help me identify the points where expressions have identical values. So this is schematically what we want to do, and to do that we will use a technique called value. We'll show what those we will assign numbers to expressions, and we will try to match them based on these. So let me walk through an example, and it can be used for eliminating common sub-expressions, controlling propagation, again, making other things as well. So let me explain how to do this. So we make a value number table where every variable we will put a value number. A value number is a placeholder serial number which denotes the variable. Then we will have a name table entry which will have the name list, and in terms of whether it has a constant value, and it will have a flag to show if it has a constant value. And finally, we'll have a hash table of expressions with value numbers. I'm sure this does not mean much to you. So, example. Now, before we get into the example, let us see what we are trying to do. It is a code, piece of code, which that if I translate this into not does not change. P star J is T3, I star A is T4, is T3. So kind of a little bit smart one. I mean, this is done just to keep things simpler at the beginning. Now, if you go through this, what can you say? A is 10. So at B assigned 4 star A, I should be able to reason that A is 10 and multiply 4 with A. That is 4 with 10, make it 40. Then I have I star J into T1 remains. But then I have T1 plus B. B is 40. So I should be able to put 40. Then I have T2 as 15 star A. And A is 10. So I should be able to use that as 10 and make it 150. T2 is 150. So I can put T2 here as 150. E gets I. Now T3 is E times J. So I should be able to conclude that it is I times J. T4 is I times A. So it can be I times 10. Now, if T3 is I times J, T1 is I times J, so I should be able to use T1 here. And I have T1 plus T4. So this, the code on left and the code on right are, in terms of semantics, are identical. But if you look in here, now this T2 has no use because T2 is not used. T3 has no use. So the T2 and T3 can be removed. So propagated constants, A we have propagated multiple times, B we have propagated, and so on. We have folded constant, 4 times 10 have been made into 40, 15 times they have been made into 150. So we have propagated constants, we have folded constants, we have identified common sub-expression, though it was not apparently common, I times J and E times J, but we have found out that they are actually common. And we have been able to eliminate one of them, computation of one of them, which is significant. We have eliminated another multiplication. So we have been able to identify local common sub-expression. Then finally, we have been able to remove the dead code because T2 and T3 are not used. Okay. So the simple examples show that a number of different optimizations in terms of the 3-address code can be carried out very easily. Now, the question is, all this we have done by how do we put it in terms of the algorithm? And that is why we are using this value numbering. So I said there are 3 tables. So one is a value number table where we put on the left column, we put names of variables, and on the right column, there is a serial numbering, serial numbering. That's where the name comes. This is the value number, indexing like 1, 2, 3, 4 like this. Then put the name of the value, where on the left column you have an expression which is a binary expression. I mean, it could be unary also. It's just taken binary cases. And you have a value number. The value number is the index which tells you what is the variable into which the value of this expression will reside. The value number tells you the index in the name table. Where do you find, which variable do you find the value of? So let us start with it. So I have A assigned 10. So I get A. It is not there in the value number table, so I put it. I put A. That is the first one, so value number is 1. Then I make a corresponding entry in the name table. Index is 1. The name is A. I know that the value is 10, so I put that it has got a constant value 10. Good. Now I get B assigned 4 star A. So B is not there in the value number table. So I put B, put it a value number 2, put 2, put B there, and I look up A in the value number table. I get 1. So using these two tables, I can very easily find out that A has a value 10 at this point. So what I do, I fold the constant. I multiply 4 with 10, and I know that B has a value 40 at this point. Great, right? Now I have T1 assigned I star J. None of them exist one by one, so I insert I, insert J, insert T1 in value number table 3, 4, 5. I insert 3, 4, 5. They have I, J, T1. Forget about what is written after the comma. That's not happening. So I have I, J, T1. Now this is an expression which cannot be folded, right? So I put this in the expression table, the hash table, I star J. Now where will you find I star J? You will find it in T1. What is T1? Is 5. So I put a value number 5. So I star J has a value number which is 5. So if you look up the name table at 5, the value number 5, you will know that it is at T1. That's the requirement. Then I go to the next one. C assigned T1 plus B. T1 is already there. It's got a value number 5. B is already there. It's got a value number 2. And from 2, I know it is 40. From T1, which is at 5, I know it has no specific value at this point. Therefore, I can say that T1 plus B can be simplified. I can propagate the constant 40 which B has, and this gets simplified to T1 plus 40. So this expression becomes T1 plus 40, and this is an expression. So I put it in the hash table, T1 plus 40. And where should it go? Wherever C is. C was not there, so I put C here. The value number is 6. Forget what is after comma. At 6, you have C. Therefore, T1 plus 4 is 6, because you will get the, T1 plus 40 is 6, because you will get the value of this expression at value number 6, which is. Then I have T2 assigned 15 star A. A is value number 1. Well, from value number 1, I know it is 10. I propagate that. I get a constant expression 15 times 10. I fold the constant. I get 150. T2 is not in the table, so I insert T2. That is 7. I insert 7 in the name table. That is T2. But I have got the value as 150. So I put 1. Then I go to D, assign T2 plus T2 star C.
Sir, the slides are not working. Can you please check?
You cannot see the slides?
Yes, sir. Like the slides are stuck.
Yes, sir. After rejoining the meeting, also the screen is blank. Actually, your screen sharing is not exactly working as of now.
I'll stop and share again. Let's see.
Yeah. Can you go out and come back?
You see it now?
Yes, sir. The slides are visible now.
Okay, good. So now we are at T2 we have computed. T2 is at 7. At 7, T2 we have 150. Now D is assigned T2 times C. T2 times C. T2 is 150. So this is 150 times C. C is at 6. At 6, C does not have a value, so this cannot be folded. So this becomes 150 times. So I get an expression 150 times C. I entered that in the hash table, and that will go to D, which has to be entered in the value number table as 8. 8 is D. So 150 times C gets a value number which is 8. Okay, up to this point, good. Now I is assigned to E. Now E is not there in the value number table, so we enter that has to get a value number. Now I is there in the value number table. Now I is being assigned to E, so instead of giving E a value number which is 9, I do a shortcut here. I say the value of E is same as the value of I. So instead of giving E a value number which is 9, I give it a value number 3, which is a value number for I. So this is where I'm making use of the fact that a copy is being created. So now if I look up for value number 3, I will not only get I will also get E. So the fact that E has got a value number 3 is updated on the name table, that on 3 along with I also put E. That is, two variables, E and I, have the same value. Right? So that is what I have achieved. Now let us look at T3 being E star J. What is E? E is value number 3. What is J? Is value number 4. So in terms of E, which is value number 3, if I look at the name table, I know it is I. That is, I take the leading, that I take the first variable from this, just to be consistent, because that is the oldest used. So I know that what I have is value number 3, which is I, times value number J, value number 4, which is J. So what I have is actually I times J. So I know, okay, here I have I times J. I look up the hash to enter. I find, oh, I already have I times J. So in the hash table, when I hash, I'm actually hashing with I times J. Because by looking up E at 3 and coming to the name table at 3, I've got that the leading variable here is I. So this expression actually is I times J, and I hash with I times J, I get 5, which is T1. So I can conclude at this point that whatever this expression is computing is whatever is T1. And if you look at 5, I have T1. So all that I have to say is T3 actually is a copy of T1. So I put 5 as a value number of T3, not 9, because I have concluded by looking up the hash table that the value number 5 is actually T1. Value number 5 is T1. And so the value number for T3 will also be 5. It represents the same computation. And to show that on the name table, I put T3 on here. So eventually, I have at this point eliminated the common star expression. Then I have T4 as I star A. I is 3, A is 1, which is 10. So I can propagate the constant. I get I star 10, and T4 is not there. That's entered. I star 10 is put in the hash table with the value number 9, which is the value number 40. Finally, I have C assigned T3 plus T4. T3 is value number 5, T4 is value number 9, which I have got. Now, what is value number 5? Value number 5 is T1. The leading variable is T1. The oldest variable is T1. So this is T1 plus T4. That does not exist in the table, so I enter, and I get a value number, which is a new one, which is 10. Now, C gets another value number, which is 10. Why is C getting a new value number? Because though it's the same variable, it is actually getting a new value. That's the value number. You are not just numbering variables, you are numbering the value. So C earlier had a value number 6, which was whatever was computed from T1 plus 40, which was value number 6. But now it has T1 plus 4, which is value number 10. So you have value number 10, you have another C, which is to be used when you have value number 10. So this now becomes T1 plus 4. So this is what we have achieved. And if you just go back, a bit, and if you look through this series of what we manually have done, you'll see, you can check yourself, you'll see that these all have been done at this point. So along with this, what you can also do, you can keep a track of whenever you are using a variable from the value number table, you can put a flag to say that it has been used. So if you do that, then you will see that A is used, B is used, I, J, all these are used. But you'll see that T2 will never get marked because T2 has never occurred in terms of generation of this code. Similarly, you'll find that T3 has not been used. So if you look at what are the variables that have been used, find that 2 and T3 will not be marked as used, and therefore we'll remove them from the you will get a more optimized code. In the following 2 slides, I have actually explained, taking different examples. I mean, not each step, but all distinct steps I have explained to show you what this computation is to be done. Let me stop at this point and see if there are questions.
Sir,
Yes.
in slide number 25, in the last slide, just you were sharing, slide number 25.
Yes.
Sir, can you just explain once again how exactly at the value number 150 into C, how we know that it is going to be the index 6C or index 10C? So which C would be used at value number 8, which is 150 into C in the hash table?
150 into, no, this is going serial, right?
Okay.
So that has not the entry at 10 has not come at that point. So when we are entering 150 into C, you are processing quad 5. I'm sorry, quad 6. Okay. In quad 6, you got T2 as 7. From 7, you got it at 150. So you have propagated that constant. You have got 150 times C. Now at this point, this 10 is not there against C. At this point, it is 6. Right? So it is a 6 that's what we are going to get at this point. This is a dynamic process. Right? So once just look at it this way, there are 2 things that can happen. One is 2 variables can get the same value number. As long as they have the same value number, they are representing the same value. So for example, what will happen if E is assigned 5 after this? After this, if E is assigned 5, then certainly E will not remain same as I. So I will have another entry 11 for E. I'll have 11E and I'll have E 3, 11, which will tell me that subsequently whenever I use E, I will use actually 11. For example, after quad 10, if I have use of C, then I'll look up C and I will not take 6, I will take the largest one, which is 10, which is the latest one, right? So it is going in the sequence, so it is in that order. Does that make it clear?
Yes, sir. Thank you, sir.
Okay. So you can have two cases. One is when two variables have the same value number, they are copies. As long as they I mean, any one of them is not changed. If one of them is changed, then again that gets a new value number. The other could be that one variable has multiple value numbers, which show that according to the flow of computation, the value of that variable has changed, and kind of you are taking that to be as if it becomes a different value. It becomes a different variable at that point. So you will always have to take the latest value number of a variable, and when you are looking up for variables which are alternately available, you'll have to take the leading one so that you can get the common size. That's the basic.
So there is a query by Tanmoy. He could not hear the explanation of the hash table.
What is the query, ISG?
Why was hashing table used? I could not listen because of audio problem.
So hash table is used because in using the hash table, we are trying to find out if two expressions are same or not. How do you find out if, for example, here we got in 3 we got I star j, so we have entered that, and later on in 8 we got E star j. So E star j, so I star j, whatever I'm writing here as I star j, is actually value number 3 times value number 4. So that's the hash table representation. Value number 3 times value number 4 is value number 5. That's what here I've written it as ij so that we can understand. Now when we are doing E times j, E is value number 3, j is value number 4. So E times j is also value number 3 times value number 4. So you need to find out, does the table have an entry which is value number 3 times value number 4? So it is a hash table just for efficiency. You could have done a linear search. You can just keep on matching like that. Whether because it's a binary expression if you start with. You can have unary also, but how do you say that the two expressions are same? The logic is their operator has to be same, which is easy to check. Then their left operand, the value number of the left operand and the value number of the right operand has to be identical. So there are 3, this triplet has to be same. So how do you check whether the same triplet exists in the hash table? You can do a linear search and find out. That's, in general, this turn out to be large. So, and you are doing thousands and thousands of such things. So you do not want the inefficiency of a linear search. So you are doing a hash table. Hash table has no specific significance in terms of the actual computation. But it's a hash table because you have to search on this. On the other two, it is easier. Possibly you can kind of index. Does that answer you, Tanmay?
Tanmay not responding.
Is there any other question, ISG?
Let me see. No, nothing more.
So let me go forward and complete this. So again, I have taken the same code same high level code, but the codes that I have here are the codes that are generated in our style. So like instead of earlier we had simply A star 10 and B star A. That is not what will happen in our case. It will have T1 assigned 4 star T and T1 going to B. So some more temporaries will happen, and this is a longer code that we get. And it is worked out here. I do not want to work through this, but I will suggest that you work through this. That you will find that you get this code generated. I mean, this is the optimized version that you get, of which you'll be able to easily see by marking the use that quad 2, similarly quad 6 can be removed. This instance of C has no use. Quad 7 can be removed. P4 has no use. Quad 11 can be removed. So these can be removed. And then you can propagate some of the copies between 8 and 9. Like this is T5 computed here, T5 here. So you can actually replace this T5 by D. That is a P4 optimization. You can do similar thing between 13 and 14. You can replace C by this and remove that. And if you do that, these two, then your code will eventually turn out to be the same as what we got earlier. So this is just to illustrate that even with our style of generation of code, as you go through this value numbering strategy for local optimization, we'll be able to optimize common sub-expressions, propagate constants, hold constants, and remove the dead code. One point to note that when you do the useless marking, make sure that you do not remove quad 10, because E is a copy of I as a user-defined variable, and you do not know it may have further use later on, right? So E kind of will be considered a live variable. We will talk more about that, but that's not something which we removed in the. We did not say that we can remove this here either, and we can remove that in here as well. Okay? So that's kind of a workout example that you should do. I've worked out here, but please try to do it yourself so that you'll get something which will come to you again and again. So if I go back to our original example of vector product, then these are the two blocks. Block 4, where we discussed between T4, T6. Block 8, where we discussed between T8, T10, and T12. You will have local common sub-expressions. And again, in the next two couple of slides, I have shown using value numbering, you can optimize them. You can get the local common sub-expressions eliminated. Similar worked out for block 5. Again, these are all workouts, so please work it out yourself by hand and look up. So locally, the common sub-expressions, copies, and dead codes can be taken care of by this method. Right? And after having done those optimizations, this is the final code, which is locally optimized, is what you get. So you can, we'll further work on this based on the global. Now, a couple of other things related to this. For example, in place of I plus j, if I get j plus I, would I be able to handle that as a common sub-expression? Well, if you know that plus is a commutative operator, then while searching the hash table, you could always, while searching for I plus j, you could also search for j plus I. So similarly, you can, hold simple constants like adding 0 or multiplying by 1. These kind of things can be done very easily. So these are the extension of things that we can do. But just a word of caution. Suppose you have a code piece like this. X assigned AI, AG assigned Y. This could happen within one basic block. Now the question is, can you do this optimization? Can you put X into Z? The size is not changing. The point is, you cannot do that because when you are assigning Y to J, AJ, you need to be sure that I and J are not same. It is easy to reason that they are copies, but if I and J are not copies, you cannot conclude that I and J are different. They can still be the same by value in some execution of the program. So if you do that, if you do this optimization, you will go wrong because the value of AI has changed because J was having the same value as I, so it has become Y. So if you reuse X to assign to Z, that will be an error. Right? So it is just to warn you that, well, these techniques work well when you do not have references. But the moment you have references, this is an array case. A similar case can be formed for pointers. So when you have those, then certainly doing, the moment you assign to some pointer, possibly all pointer values that have been copied has to get invalidated. And we'll see more of this concept coming in when we do the data analysis. So just a word of caution that this value numbering scheme, which is very attractive in terms of local optimization in basic blocks, can run across basic blocks very easily, are not may not be blindly applicable to references when you have arrays and pointers. Similar things you could have in terms of okay. So this is basically about value numbering. Before I close, I would just give a glimpse of what one of you said, that whether basic blocks can be merged. Now, naturally, basic blocks cannot be merged, but several algorithms will use basic blocks, kind of an extended definition of a basic block, where you assume single entry but multiple, like you have it here. Now, this basic block B1 has a single entry. It has 2 exits. This also has 2 exits. But this block has multiple entries, multiple points, coming from multiple points. So you can see this B2, B3, B4, B5, B6 kind of forms a tree, but the control necessarily enters at one point and goes out through one. But the control cannot come from it. So often you could treat such, segments of code as one unit. It could be a linear flow. There is no loop back in this. This is always a forward flow. The difference is the moment you merge, there could be, multiple forward and backward flows coming in. But if you have this kind of a tree, it is always a forward flow. So many of the simple basic block algorithm could be extended for these cases. So these are called extended basic blocks. We will not do any specific algorithm based on that. I just want you to know. Maybe at some point we'll make references to such basic blocks as well. That's all I had in this module. Let me stop and ask if we have any, check if we have any questions.
For the theory class, you will again be meeting after the vacation.
In the theory class, we will meet, I think, on the next class is probably on 2nd
2nd November, yeah.
The next week, both Monday and Tuesday are holidays. So we'll have the next class on. So before vacation on theory, we are closing with module 8. So after vacation, we'll start on the module 9.
As we are having that lecture as per schedule.
Right? Now I wanted another input is I saw your feedback to the faculty advisor, and there was a suggestion that we should take theory on Saturday and tutorial on Monday. We have a few left only, I know. But if you want, we can do that. I mean, I have no problems doing that. Because even though the tutorial was put on Saturday for 1.5 hours, I typically see that we get wrapped up within 1 hour. I'll request your representative to finally have a kind of consensus amongst you. And if you want this change, then please let me know. Because in that case, 31st October, which is a Saturday, is a tutorial class next. The tutorial class this week is vacation. So if you want the change, then on 31st October, I will take a theory. And on 2nd November, on Monday, we will do the tutorial. So I'll request your faculty, your class coordinator, class representative to finally take a consensus, and because I just saw that from Professor Ravitra Hajra on the comments. We did not get because we have been meeting so regularly, and you haven't mentioned me that this was an issue. So if it is a consensus issue and you really want the change, I will request the representative to send me a mail to that regard. If I do not get a mail, we will continue to have theory on Monday. If I get the change mail, because you know that accordingly the teams setting and all that needs to be changed. So it's not just that we come to the class and do something different, because tutorial is a split class. So whoever is the representative, I'll request that if you want the change, then please let us know through mail. Otherwise, we will continue as we are. Any question otherwise?
Doesn't seem so.
So this Thursday we will meet, right?
Yes.
And you are going to teach on the continue on the runtime environment.
Time environment, yeah.
And we will not have any submission, but we will assign assignments. Okay. Thank you then, friends. Thank you very much. Have a nice day, and till we meet on Thursday next. Bye.